So far, we've learned two different types of line integrals, which are integrals over parameterized curves. We have learned about line integrals with respect to arc length, which here the integral over c of f ds is the integral from t is a to t is b of f of r of t, magnitude r prime of t dt. And then the integrals with line integrals with respect to x or y, we have the integral over c of f dx is the integral from a to b of f of r of t, x prime of t, and symmetrically the integral with respect to y is the integral from a to b of f of r of t, y prime of t. So line integrals are integrals evaluated along a curve, and the value of any line integral is the sum of the values of the function to be integrated, which is f here, at all points along the curve, and it's weighted by some sort of scalar function on the curve for these two. For the line integral with respect to arc length, the weighting is the magnitude of the velocity vector. And for the line integrals with respect to x or y, the weighting is the x or y component of the velocity vector. So today we're going to learn the third type of line integral, and that is a line integral of a vector field. Okay, so for a line integral of a vector field, let's let C be a parameterized curve in the xy plane, or in R2. And then for every value of t from a to b, there's a point, x of t, y of t, on the curve C, where we could say that r of t is x of t, y of t. So r of t is x of t, y of t. Okay, so let's let f, we'll use capital F here, be a vector field that's defined in some domain D in R2 that contains this curve C. Okay, so maybe D is a vector field that looks like this. Or I'm sorry, D is a domain that looks like that. And C is inside of that domain D. Okay, and let's let our vector field f of xy equal p of xy, q of xy. So then maybe at every point inside D, there's a vector for this vector field. Okay, let me get another color here. All right, so maybe my vector field looks something like this and that. We'll just draw some kind of random vectors here. Okay, so I've got perhaps what a vector field might look like in this domain, okay? And the question is, how do you calculate a line integral over a vector field? So, definition, the line integral over C of f dot dr equals the integral from t is a to t is b of f of r of t dot product r prime of t dt. Okay. So what is this dot product of two vectors, f of r of t dot r prime of t? So given some t value on the interval from a to b, we have the dot product of a vector field f at a point r of t and the velocity vector r prime of t. Now, the dot product is going to give a scalar number that is a function of t that can be integrated from a to b. So what does this definition mean? What is this integral finding? So what this is finding, well, let's start by drawing some velocity vectors. So this is the velocity vector. Okay, that's the velocity vector at any point r of t. So you can see our curve C goes from this point to this point. Our starting point is x of a, y of a. Our ending point is x of b, y of b, where t is going from a to b. So at any point along the curve, our velocity vector should point in the direction that the curve is heading. So our velocity vectors are going to look like this. And this actually makes a lot of sense, sort of what this calculation is doing. The integral is giving a measure of the degree that the vectors in the vector field are pointing in the same direction as the tangent or velocity vectors on C. So for example, if we look here, the velocity vector, let's make this a little darker, our velocity vector is pointing very much in the same general direction as the vectors near it in the vector field F. Now, when they're pointing in the same direction, that makes a positive contribution to the integral, okay? Over here, you'll see that if I look at that tangent vector, these are almost perpendicular. This vector in the vector field and this velocity vector. So obviously when we dot product things that are perpendicular, that's a zero contribution. And then over here, you can see that this velocity vector and this vector in vector field F, they're almost pointing in opposite directions, and that's going to give a negative contribution to the value of the integral. So you can think of positive contributions as happening when the velocity vectors are sort of going with the flow of the vector field. They're heading in the same direction as the vector field. And negative contributions when the velocity vectors are going against the flow of the vector field. And I'll talk a little bit about sort of a physical interpretation of what's going on in a few minutes. Okay, so what's interesting about this vector version of this integral is this can also be written as in terms of two integrals with respect to x and y. So let's see how that happens. So we're starting with the integral over C of f dot dr and that equals the integral from a to b of f of r of t dot r prime of t. Okay, so, well, I can write this in its component form. So f of r of t, remember I defined f up here as p of xy, q of xy. So that is p of r of t, q of r of t, and then dot, the velocity vector can be written in its component form as x prime of t, y prime of t, dt. So now if I actually dot product these two vectors and write out what I get, I'm going to get p of r of t, x prime of t, plus q of r of t, y prime of t, dt. Well, let's separate this into two separate integrals. So this is the integral from a to b of p of r of t, x prime of t dt, plus the integral from a to b of q of r of t, y prime of t dt. And now you can see this is an integral with respect, a line integral with respect to x, and this is a line integral with respect to y. So our line integral over a vector field can also be written as a sum of an integral with respect to x and an integral with respect to y. So this is the integral from a to b of, this is p dx plus q dy. Okay, so now let's go back and think more about what this integral is finding and relate it to the picture that we've drawn up here. So the physical interpretation is that if F is a force field, then the line integral over C of F dot dr is the work done as you move along the curve. Okay, so imagine that in my picture, C is a road and F is the gravitational field. Okay, if the vectors in F and then C's tangent vectors are pointing the same way, imagine that you're riding a bicycle downhill and the gravitational field is helping you move along the road, so you're doing less work. So that we might imagine is happening right here. We're going downhill on a road. Now over here, where the vectors look more perpendicular to each other, the road would be flattening out, and then here it looks like we might even, where the vectors are going opposite directions, imagine we're starting to go uphill and we're going to need to pedal harder because the gravitational field is slowing you down. Okay, so that is, let's sort of summarize the three types of line integrals that we have now. So I'm going to summarize looking at our formulas in 3 dimensions, because all line integrals work analogously in 3 dimensions. So let C be a curve in R3, where t goes from a to b. Let f be a function on C that gives values in the real numbers, and let capital F be a vector field PQR that's defined on the curve C. So we have our three types of line integrals here. We have our line integral with respect to arc length, analogous formula in 3 dimensions, our line integrals with respect to x, y, and z, and lastly, our line integral over a vector field, all written in 3-dimensional formats. So let's also review the extent to which each of these line integrals depends on parameterization. And I'll do a few examples to prove it or to show how that works, not proving it, but to show how it works for this one. But we've already talked about that for a line integral with respect to arc length, this integral is independent of the parameterization of C as long as there is no backtracking. You cannot go over any part of curve C more than once. For both line integrals with respect to x, y, and z and line integrals over vector fields, they do not depend on a parameterization even with backtracking, but if you switch the orientation, the integral is multiplied by -1. So for both of these types of integrals, the line integral over -c is equal to the negative line integral of c. And this makes sense here because these same behaviors you would imagine occur because this second type of integral, these can be written as line integrals with respect to x and y, the sum of a line integral with respect to x and y, the integral over a vector field. Okay, so in another segment, I'm going to do several examples calculating the line integral over a vector field.